Okay, the nucleus of polonium-210 emits an alpha particle and forms a lead-206 nucleus, as shown in the equation below. Calculate the energy released during this process. We've been given the mass of the polonium, the lead, and the alpha particle, so we're going to have to find the mass defect. Take the mass of the polonium, subtract the mass of the lead and the alpha particle, and you get a mass defect of 0.00581 atomic mass units. We know that one atomic mass unit corresponds to 931.5 mega electron volts. So if we multiply by that, we get the energy released in mega electron volts. If we want it in joules, times it by 10 to the 6 to 10 electron volts, and then times it by 1.6 times 10 to the power minus 19, and then you get the energy in joules. Okay, tritium and deuterium are isotopes of hydrogen which are used in nuclear fusion experiments. Calculate the energy in joules released when tritium nucleus undergoes fusion with a deuterium nucleus. We've been given the equation here, and we've been given the mass of the reactants and products. I'm going to find the mass defect. I'm going to take the total mass of the reactants, which is the hydrogen and deuterium, and I'm going to subtract the mass of the helium that's produced and the neutron that's released as well. That gives me a mass defect here in kilograms. And if I want to turn that into an energy, I'm going to use Einstein's equation equals mc squared and times it by the speed of light squared. And that gives me the energy in joules released during this reaction. Okay, uranium-235 can be induced to undergo nuclear fission to produce barium and krypton and some free neutrons. Complete the equation and calculate the energy released in this process. Okay, so neutrons don't affect the proton number, so I'm just looking at the max number. We've got 235 here and 1, so that gives me 236 in total on the left-hand side. And we want 236 on the right-hand side as well. So 89 plus 144, that's 233. So we need 3 more, a mass number of 3 more. So that's going to come from the neutrons here. So we need at least 3 neutrons. Okay, we've been given the binding energy per nucleon of the different nuclei involved in this. Okay, so in this case, we can't find the mass defect. Instead, we're going to have to find the difference in the binding energy on the left and the right. So firstly, uranium-235. It's got a binding energy per nucleon of 7.5. So we're going to multiply that by 235, the number of nucleons, to get the total binding energy for uranium. Okay, and then the neutron, the free neutron, has no binding energy. Okay, binding energy is the energy required to split a nucleus into its constituent nucleons. So if it's a neutron, it doesn't have any binding energy. Okay, if it's a free neutron. And then we've got a krypton on the right hand side here. So that's got 8.6. So we're going to multiply that by 89, the number of nucleons. And then with barium, we've got 8.3 times 144. Okay, and finally the neutrons are again the free neutrons, so they've got 0 binding energy. So the total on the left is 1762.5, and we've got the total on the right. If we calculate that, we get 1960, and the difference here is the energy that's released. So I just subtracted the difference there.